In this video we're going to see how to determine the price of a European call option using the Monte Carlo method. So we start by importing the libraries that we will need, so NumPy. From SciPy we import stats and we import matplotlib .pyplot as plt. So we start by defining this function, that is the geometric Brownian motion simulations. So we will need these parameters, the initial stock price for the dynamic we want to simulate, the risk-free rate, the volatility of the underlying, the time for which, the time horizon for which we want to make the simulation, the number of time intervals for each t, and then we define the number of simulations as m. So now we can define that dt as t divided by n. By the way, I published a video in this channel on geometric Brownian motion previously, and if you want to watch it, I put the link here. Then we define tt as np.arrange. It will be our time vector that starts at 0, stops at t plus a small quantity, so that the final t will be included in the interval, and with the step we've just defined, that is dt. We define then n as the length of tt. Then what we want to do is to simulate the dynamics. So we initialize the array S, that is np.zeros with shape equal to n rows and m columns, that is the number of simulations, with the first element of S being the parameter S0 that we defined for the function. Then we want to define the random part of the dynamic, and we do that by using the stats module, stats norm or vs, with size, that is n minus 1 rows and m columns. We put n minus 1 rows as the first row is already defined as S0, so we do not need a random component for that. And we multiply it by the square root of dt. Then we can write our loop for e in range n minus 1 as before. We want to simulate n minus 1 stock prices, so we put n minus 1 inside the range function, and so we defined the I plus 1 element for each column of S as the previous value multiplied by np.x r minus 0.5 volatility squared multiplied by the t plus the random component, that is the I element in dv multiplied by the volatility. Okay, and we want this function to return the S we just defined. Then we want to write another function, that is call price, with a 95% confidence interval for the option price. So we do not just want the point price for our simulation, but we will make quite a lot of Monte Carlo simulations, and for each simulation, depending on the number of trajectories in each simulations, meaning varying this term m, we will see how the point price of the call will change. So, for example, we will draw a simulation of 10 trajectories, and we will see the call option price for that. We will then draw a simulation for 10,000 trajectories, and we will see how the precision of the simulation will improve. So we need a 95% confidence interval. So we will put inside this function all the parameters that we set for the previous one, adding also the strike price for the option. So now we will draw all the paths, recalling the function gpm. This is our array S that contains all the simulation paths. And then we will need to calculate the discounted payoffs. So what we need, so is this element payoff discounted, that is given. Remember the payoff for a call that is S, the maximum between S minus K and 0. So we write np.maximum. We take the last element for each simulation. So we take the last element of path. We will see all the last elements that we've simulated. We subtract k and the maximum between this quantity and 0. And we want to discount it, so we multiply it by the exponential of minus r and t. So then we obtain the price of the call as the mean between all the discounted payoffs. So right now we have the value of the call for a certain simulation with m trajectories. But we said we also want the confidence interval. So what we need is, firstly, we calculate the standard deviation with the NumPy function std, so on the payoffs discounted. Then what we want is the standard error that is given by the standard deviation divided by the square root of the number of simulations that we calculated, and then we can calculate the down limit as the call price already defined minus 1.96 multiplied by this standard error. So the 1.96 is related to the normal distribution for a 95% confidence interval, and we do the same thing for the up limit. So the up limit is the same, but we have to add this quantity. So right now we have our function that returns not only the call price but also the down limit and the up limit. Then what we will do is to start writing our parameters. First, we set a random seed as, for example, 1002. And we say, for example, that S0 is 10. The risk-free rate is 2%. Volatility of the underlying is 40%. We want a time horizon of 1 year, and we divide this time horizon in 500 intervals, and we set the number of trajectories we want to simulate as an array that contains these values, for example 5. And by the way, these 5 I put here does not really define a Monte Carlo simulation, but it will be interesting to see, for example, what happens if I draw a simulation with so few values. So 500, 1000 simulations, 5000 simulations, 10,000 simulations, and 20,000 simulations. We will see how the call price and the confidence interval varies based on the M values. And we define the strike price for the call option as 12. So right now we should define these, we should initialize these arrays. So NP zeros, we give it the length of M. So it will be an array that contains 7 zeros as the values of M, and after we will finish writing our code, we will have this object that will contain all the call option values for each of these Monte Carlo simulations. So we do the same thing for the up limit and down limit as so these will contain all the down limits for each one of these Monte Carlos, and here we will have the same. So right now we will use the enumerate function. So for I value in enumerate M. So this I is the index and it will have the values 0, 1, 2, 3, while this value will have the exact values we put inside M. So it will have for the I equal to 0 a value of 5, for I equal to 1 a value of 100, and so on. So for I value in enumerate N, we want calls I to be valued at the call price with confidence interval. Okay, but first let's define the results for our function. Up limit equal to, I made a mistake here, so let's put it here with obviously all these parameters. Okay, and we put a value inside of M, so that we will draw Monte Carlos with we will draw 7 call values for each of these number of trajectories, this value. So we will start filling our array calls with all these values that we get. So equal to call the limit I is equal to down limit, and the up limit I is equal to up limit. So we can also do this thing that is, for example, we want to print at each cycle the value of the call option with the confidence interval. So we use an F so that we will see what that means. So the European option value for a Monte Carlo simulation with value trajectories. So for each cycle, this value will be replaced by these exact numbers inside the M array. So we write the ith element on the calls array, and we want 4 decimals with 95% confidence interval defined as we put the d limit here with 4 decimals and the other value for the up limit, that is this. That is it. And then we will run all this code to see if everything works. Then we can draw the graph plt.subplots. Then we write plt.errorbar. We want to make a graph with m on the x-axis and with the calls values on the y-axis, with these parameter where we can put our intervals. So that is calls minus the limit up limit minus calls, and we want these here. Then we write a title. We want a plt.xlabel.y labels. So let's see if everything works fine. I hope to have written everything correctly. Okay. Then we run all this part. Okay. I believe that's right. So as you can see, for a Monte Carlo simulation with 5 trajectories here, the value is 0 because for all these 5 trajectories, the price dynamic never surpassed the strike price. So the option value here is 0, and also the confidence interval is 0, as we really don't have any standard deviation. All the option values for every trajectory is 0. Then, as we increase the number of trajectories in our simulations, the price becomes closer and closer to the actual value of the European call, with the 95% confidence interval that restricts more and more. But here we have an error that is, why do we have these? Down limit, up limit. Yeah, obviously I made a mistake here. I put 2 up limits, so let's rerun this code. Okay. Now we have the right confidence intervals, and as you can see, as we increase the number of trajectories, the confidence interval becomes narrower. Then we draw our graph. Okay, and this is exactly what we meant. For 5 trajectories, we have a call option value of 0. That's the reason why we need a lot more trajectories for our Monte Carlo to understand the real value of the option. As we increase the number of trajectories drawn for every simulation, then as we increase the number of trajectories in our Monte Carlo simulations, the confidence intervals become more and more precise.